Okay folks, so I want to go ahead and do a video solution to number 34, which is the question, hey, given a second order linear ODE, the first question is simply to give a solution set for it that we think is a basis, but then the second part is to prove that we've actually found a basis, and in this we are not to assume, so do not assume that you know the dimension of the solution space. So let's go ahead and first just give the solution. So we're looking at x double dot plus 25x equals 0, which has the characteristic equation r squared plus 25 equals 0 with roots plus or minus 5i. And so we've said then that x of t has as a solution, well, we've been given the general solution. This is what we've been writing as the general solution for this, but what we're being tasked with here is basically proving that this is the general solution. So the cosine of 5t plus c2 sine of 5t. So really here are two solutions, right? x1 of t is the cosine of 5t is one solution to this ODE, and x2 of t equals the sine of 5t is a second solution. So these are the pair of solutions that we think will be a basis for the solution space S. Okay, so here we have our guess. The cosine of 5t, comma, the sine of 5t. So again, in this problem, we're not assuming that we know that two linearly independent solutions is enough to give us the entire solution space. So we can't really say that this is a general solution in this problem, even though we've been operating under that assumption. So this problem is asking us to prove what we've been using. So let's go ahead and do this. We're asked to prove that our set here is indeed a basis of the solution space. So we're asked to prove that the cosine of 5t and the sine of 5t, that set together, forms a basis for our solution space. So remember, we need to prove two things. First of all, we need to prove, let's go ahead and give this a name, let's call it B. We need to prove that B spans S, that's the first thing, and we need to prove that B is a linearly independent set. So we need to prove that B is Li. Okay. Of these two, this is definitely the harder task, and that's what we're going to jump into first. Okay. So we said this the first time we did this in class. How do I know that there isn't some crazy function out there that I've not considered that is also a solution to this differential equation that isn't of the form c1 cosine 5t plus c2 sine of 5t. I mean, there might be some crazy Taylor series polynomial. There may be some crazy integral equation that we've not considered. There might be some sort of solution that we've not considered for this differential equation. How do we know they can all be written this way? Well, to do that, we've got to show that any solution to this differential equation, here, can be written as a linear combination of these two vectors. Okay, so what are we going to do? We're going to just say, let's let phi of t solve the ODE. And this ODE is x double dot of t plus 25 x of t equals 0. So what do I need to do? So our task, you don't have to write this, but our task is to show phi of t is equal to c1 cosine 5t plus c2 sine of 5t, but we don't know that. Okay, so this is our goal in trying to prove this. I'm trying to prove this first bullet point here. Okay. So we know that phi of t naught, plug in some t naught into this function, and it's going to spit out some a value. And we can take the derivative of this function because it solves a differential equation. We have to be able to take its derivative. We can take the derivative of this function, and if we plugged in the same t naught, it's going to spit out some other real valued number. What does that mean? That means then phi solves. We already know that it solves the ODE. That's how we picked it. But it also means that it solves the IVP, the initial value problem, x double dot plus 25x equals 0, and x of t naught equals a, and x dot of t naught equals b. This IVP, phi of t, we know it solves the ODE, that's how we picked it. And we said that, well, when we plug in some time value, it'll spit out a functional value. We plug some time value into the derivative, it'll spit out another value. And so it's going to solve that corresponding IVP. Okay. So again, our task is to now show that this phi of t that satisfies this IVP can be written as a linear combination of what we're claiming our basis vectors to be. So what are we trying to do? Well, we're trying to find some linear combination of the cosine of 5t and the sine of 5t, so that when we actually plug in the value t naught into the time value, it spits out a. And if we take the derivative of this and then plug in t naught, we would have minus 5c1 sine of 5t naught plus 5 c2 cosine of 5t naught, and we want this to equal b. So if I can find a linear combination of sine and cosine so that this is true, when you plug in t naught, it spits out an a, and when you plug t naught into the derivative of it, which I've written here, it'll spit out a b. If this has a solution, then, so if this system has a solution, then c1 cosine 5t plus c2 sine 5t solves the same IVP. So our entire problem of showing that sine of 5t and cosine of 5t and sine of 5t form a basis of our solution space boils down to saying, does this system right here with these two equations, does this system right here have a solution for C1 and C2? Well, we can write this as a matrix equation. Written as a matrix equation, this would be the cosine of 5t naught minus the sine of 5t naught. Sine, oops, I dropped the 5 there. This 5 right here. The sine of 5t naught and 5 times the cosine of 5t naught times the unknown coefficients, or the unknown parameters, C1 and C2, and does this spit out A and B. So this matrix equation right here corresponds to this system of equations here. And so we ask the question, does this matrix equation have a solution? And finally, we're down to a point where we've got a linear algebra tool that tells us quickly whether or not we've got a solution to this equation. Let's check the determinant. So if we call this A here, let's check the determinant of A. And we have a theorem that says, provided the determinant of A is not 0, then this corresponding system will have a unique solution. The system has a unique solution provided the determinant of A does not equal 0. So let's find the determinant of this system. So we've got the determinant of the cosine of 5t naught minus 5 sine 5t naught, the sine of 5t naught, and 5 times the cosine of 5t naught. And if we compute this determinant, we get 5 cosine squared of 5t naught plus 5 sine squared of 5t naught, but by our Pythagorean identity, that just equals 5, which is certainly not 0 for this choice of t naught, or in fact any other choice of t naught. So we can go ahead and give solutions for C1 and C2. So C1 and C2 have a unique solution. So let me just say the system has a unique solution. Okay. So C1 cosine of 5t plus C2 sine of 5t solves the same IVP as our general, just our randomly chosen solution phi of t. But what? What do we know about solutions to IVPs? Well, solutions to IVPs are not always unique, but since this is an nth order, linear, and that's the key word there, linear ODE, IVP solutions are unique. Therefore, phi of t, since phi of t solves the IVP and this linear combination of sines and cosines solves the IVP, that means, and they're unique, that means these two functions need to equal one another. So what have we said? We've then said that cosine of 5t and the sine of 5t, that these two vectors span S. They are a spanning set for S. So we've done all the hard work. We've got one more box to check, and what is that? What's the one box we have left to check? Well, come on, a little more space here. We've just said that the set that has cosine 5t, sine of 5t, those two vectors form a spanning set of our solution space. But what do we still need to check? So we've met this criteria, but now we need to look at this one here. We need to show that B is linear independent, but we've basically already proven that. Let's go ahead and just jump back to that. We've basically already said that when we looked at the determinant for a specific t-naught value. So all we need to do here is to show the cosine of 5t, sine of 5t, that set is Li. Look at the Wronskian of the two. Now notice here I'm not selecting a specific t-naught value. This is just the two functions to show that the two functions are linear independent. Well, we look at the Wronskian of the two, and if we compute that, we would get the same thing that we got before. We would get 5. Okay. Therefore, this set, cosine of 5t and the sine of 5t, in the part that I did in blue, we showed that it was a spanning set. In the part that I just did now in red, we showed that it's linear independent, and those are the two things we need to check in order to show that this set right here is a what? Is a basis for our solution space. Clean up that word. And so we're done with the problem. Okay. By the way, we've also shown two other things. Note that we've also shown, you don't need to write this down, but also let's see here, let's go ahead and write it this way. X of t equals C1 sine of 5t. Let me stay at the same order. Cosine of 5t plus C2 sine of 5t is a general solution. That is, any solution to the above ODE can be written as a linear combination of these two vectors. That's what we mean by a general solution. What else have we shown? We've just shown, since the basis set, the set that is the basis set, has two elements in it, we've just shown that the dimension of the solution space is 2. Okay? Which was the thing I said you couldn't assume when you started this problem. If we could have assumed that the dimension of the solution space excuse me, if we could have assumed that the dimension of the solution space was 2, then all we would have had to have done was shown that these two vectors here were linearly independent, and it would have been enough to show that they were a basis. But because we didn't know the dimension was 2, we had to show that it was also this set was also a spanning set, which was the hard part of this problem. Okay, folks, that's all I've got for this. Let me know if you have any questions.